Okay. So, you have calculated that RT60 mean free path or reverberation time, mean free path, number of reflection, all those things we can calculate for a given dimension and all the parameters. Now, there is a two kind of room acoustics. One is called large room acoustics, another is called small room acoustics. Large room acoustics and small room acoustics. The question is, when does the statistical model apply? We said that above whatever derived, we say that RT60, when the statistical model is applied, when the statistical model will be applied. Do not split the slides, let us discuss. What is when the statistical model is? In statistical model, what I said, that if the room has enough number of reflection sound, which is statistically validate that for any point the number of reflection will be equal in the room, and it create a diffuse sound field. Diffuse sound field means a reverberant diffuse sound field in which the time average sound pressure is equal in everywhere in the room. Then we said the statistical reverberation time is applied and it is a large room acoustics. So, if the room volume, if I say number of reflection n per second is nothing but a S into C by V, not S into C by V, number of reflection per second is nothing but a RPS SC by 4V, SC by 4V, sorry 4V. Now, if the number of reflection is large, then we apply a large room acoustics or reverberant sound field is created and statistical model of sound growth is applied. Now, in a small room, the resonant standing wave, so called room nodes, dominate the response. In small room, number of reflection will be less, and in that case, that it does not on the sound field is not reverberant sound field, it created by a node, room node, sound field created by a room node. Let us discuss those two things. Now, what is, how much volume is required to support a large room, or what is the large room? So, large room equation is that if FL is the large room frequency, FL is equal to K into RT divided by V. RT is nothing but a reverberation sign or RT60 divided by the volume of the room, K is a constant, FL is the large room frequency. Okay. So, suppose I want to design an auditorium for speech using large room acoustics. Large room acoustics is a reverberant field, large room acoustics, auditorium in large room using large room acoustics. Then its volume must be support, V should be FL by K. So, I can say FL is equal to K into root over of RT reverberation time by volume. So, I can say the FL square is equal to K square by RT divided by V. So, V is nothing but a K square into RT divided by FL square. FL square. So, the volume, required volume must support this equation. What is this equation? Value of K is 2000 in SI. So, V is nothing but a K square RT divided by FL square. So, suppose I want to design a speech room, speech auditorium for speech, then the FL is 80 hertz. If it is for music, then FL is 30 hertz. If the volume support for 30 hertz, that volume will support for high frequency also. The minimum volume is required at lowest frequency is response is 30 hertz, then it support in high frequency also. So, the volume required is F square by RT divided by FL square, which is the minimum, minimum volume required to support the large room acoustics for music. For speech, FL value is 80 hertz or 60 hertz, you can say the 60 hertz also, 60 hertz. So, I can say, I can give you a problem. Once a civil drawing is given to you, you have to decide it whether this volume of the room, whatever the civil drawing is given, is support the large room acoustics is not. If it is large room acoustic, treatment will be one kind, reverberation time will be calculate. If it is not, then it has to be treated by a small room acoustics. Small room acoustics, sound is developed in using a node. Okay. Large room acoustics, reverberation. So, depending on the given volume, I have to calculate whether it is support the large room acoustics or not. I have to change the volume if it is required. That is why if you see, suppose I want to design an auditorium and RT60 is equal to 2 seconds, then for music, then I can calculate the volume is nothing but a 2000 square into RT60, RT, reverberation time is 2 seconds, divided by FL square is 8, it is 30 hertz. For music it is 30 hertz, 30 hertz, 30 square. So, then I get the minimum volume which is required. So, if that civil drawing, whatever the volume is given, is support that volume, then I go for the large room acoustics, unless I go for the small room acoustics. Okay. I am not discussing. Now, if it is small room, large room we have already discussed. Large room acoustics, reverberation time, we can treat that acoustics wall to control the A. I know the reverberation time, I know the volume. So, I can treat that wall with a different absorption coefficient to calculate to reach the desired A in 7. Now, for small room, room node refer to the standing wave resonance that exists in a enclosed space. If I enclose space in a small room, it creates a standing wave. To visualize the standing wave nodes, recall the resonant nodes on a string. When a resonant frequency excited the string, a standing wave is set up. You know that standing wave generation. Let us go for an example. This node is called eigennode. What is eigennode? An eigennode is an European name of the standing wave. Standing wave are depend upon the internal dimension of the enclosure. The first node F0 is nothing but a C by 12. Why? You know that. Suppose this is a enclosure. What is the first node? This one is the first node. So, it is lambda by 2, half wavelength. So, that is why F0 is nothing but a C by 12. Okay. So, node any room dimension is, if the room dimension is L is length and W is width and H is height, then nodes are C by 2 into root over of N1 square by L square, N2 square by W square, N3 square by H square. So, if it is F1 0 0 only with the node is exist with only the length, then C by 2 into root over of N1 is 1. So, 1 by L square. Second node F2 0 0 C by 2 root over of 2 square by L square. I can calculate. Okay. Standing wave node. So, mode definition. Now, I come to the mode definition. Axial mode, the component wave parallel to an axis in one dimensional. So, suppose in this room the node is created parallel to the axis, only the horizontal, the surface, ground surface, that node is created. So, only the node is created along the xy plane only. So, or you can say it is created along the x axis only, standing node. So, that is why it is called axial node, or it may be, so I can say axial node, it may be created along the x axis, then it is n x 0 0. If it is created along the y axis, n 0 y 0. If it is z axis, n 0 0 z. So, it is along the axis, that is why it is called axial node, the component wave parallel to the axis. That is why in one dimensional axial node. Then there may be a tangential node. The component wave are tangential to one pair of surface, but oblique to other pair, that is called two dimensional. So, see that it is parallel to one pair of surface, but oblique to other pair. So, that means it should have two nodes. So, it is n x 0 n z, or you can 0 0, or so in there is a the node is exist in x and z dimension and other is not there. Similarly, x and y, z will be not there. So, that is why we call it is tangential node. Then there is a called oblique node. The component wave are oblique to all three pair of surface, that is x, y, z, 3 n x, n y and n z. Three nodes are exist. So, that is f 1 1 1 first node, f 1 1 2, maybe f 2 1 1. So, all kinds of combination will be possible, first harmonic, second harmonic, third harmonic, all combination will be possible, that is called oblique node. If it is tangential node, only two will be there. So, in x and x 1 0 1 or f 0 1 1 0, all are tangential node will be there. Okay. So, for example, I can say, suppose I given you the room dimension, I can give you an example. Let us I give an example for that node calculation. Let us I told you that suppose I have a small room dimension is 4 meter, 5 meter and 3 meters, okay, and calculate the first node, lowest axial node, So, it is n, or you can say f in any axis, which is lowest, which will be lowest, when the denominator is high. So, it is can be f 0 1 0. So, it is c by 2 root over of 1 by 5 square. Lowest axial node frequency is this. Then all other frequencies will be created. Okay. So, that is that way we can do it. Next one is small room geometry. Acceptable room ratio for a small room acoustics, that is given, that is say standard length, width and height. So, once I want to design a small studio for speech studio, small room acoustics, then I create within this ratio. Okay. Now, semi reverberant room. Now, I go for the so the small room acoustics. I will discuss the acoustics acoustic treatment later on. So, I discuss the small room acoustics. The acoustic field is created in node, and large room acoustics is a reverberant field. So, semi reverberant field, you can say that semi reverberant, there is a absorption, semi reverberant field. So, suppose I have a semi reverberant room in auditorium. How do I calculate the power and different parameters, that is here. So, semi reverberant room calculation. A room that has a mixed reverberant sound and direct sound from a source is called a semi reverberant room. So, suppose I have an auditorium, let us I draw this, let us listen. So, I have a sound source here. In here I want to calculate the power, sound intensity or sound level, sound pressure level. Then since it is a semi reverberant room, there is a direct sound and there will be a reflected sound, many reflected sound will be there. Okay. So, note the most of the real auditorium in practical purpose are semi reverberant room. So, I can say this is the direct sound. This point the sound is created or the sound pressure level will be developed based on the direct sound. So, direct sound will come here with the pressure level, then first reflection, second reflection, third reflection, fourth reflection, fifth reflection. So, that way the reflection sound will be arrived here, different reflection sound will be arrived here with a lower amplitude. Once the length is If the path is high, time will be high. If the path is high, the intensity will be less. So, intensity will be decreasing in order, and number of reflection will contribute to the sound pressure level of this point. Okay. The gap between the direct sound and fast reflection is called initial delay. Initial, I will discuss that initial delay. Okay. Now, I have to calculate the source. Suppose in this room, let us I switch on this source which has a power is LW. So, what is LW in watt? In watt, LW level sound pressure level of or sound pressure level of this or sound power of this source is LW, is the power of this source. So, if it is power, then it is 10 log LW divided by or let us power of the sound source produce a W watt power. So, power level is nothing but a W by reference W 0. So, what is W 0? Reference is 10 to the power minus 12 watt per watt or watt. If it is I, then it is watt per meter square, 10 to the minus 12 watt. So, if I say let us 3 watt acoustic source, then it is 10 log 3 by 10 to the power minus 12 dB in dB. In dB. Okay. So, non-directional sound source is a free field. So, suppose this sound source is no directional sound source, it is a non-directional sound source. So, this direct sound intensity in here will be, so at point LP, let us sound an LP at this point, this is LP is equal to LW plus 10 log 1 by 4 pi r square, distance from source is capital R. At r distance it is LP. So, it is 10 log, reference power is LW, distance from R is R. So, it is why it is 4 pi r square, because it is power, it is not intensity, that is why it is 4 pi r square. Okay. Reference power 4 pi r square. So, I said this is nothing but a 4 pi r square. Now, if I put the directivity, if it is not, I said it is not directional, then it is. If it is directivity I put, then LP is nothing but a LW plus 10 log Q by 4 pi r square. Q is the directivity of the sound. What is directivity? What is directivity? Suppose if I produce a sound in here, if I produce a sound in here, it is spherically propagated. Now, if I block one side, what will happen? That energy will be reflected from the block surface and contributed in this word. Now, I give a direction to the sound in this direction only, not this direction. So, I introduce directivity of the sound. So, what is directivity? The definition of directivity Q is nothing but a ID by IO. It is omnidirectional sound intensity, directional sound intensity. So, directional source ID divided by omnidirectional source I 0. So, if this reflector is not there, intensity in here is I 0. If the placing the reflector it is ID, then the directivity factor is Q is nothing but a ID by I 0. Q in dB, Q in dB is nothing but a 10 log Q ratio, 10 log in dB. Directivity, that is called directivity index. Directivity, this is directivity and this is directivity index. So, this is directivity factors and this is directivity index. Okay. Now, let us say, see this example, that I have a wall and I have a source in here. So, what is that? This side power is channelized to this word So, how much dB will be the gain on the, how much dB the sound power will be increased? Double, half portion I channelize this way. So, it is 3 dB. So, Q is di, directivity index is 3 dB, or Q is equal to 2. Okay. Now, if I put the loudspeaker in here, this corner, this is a 2 surface, then what will happen? Once I put a surface here, then a sphere is cut down by this portion. So, it again increased by 3 dB. This portion is again channelized to this direction. So, it is 6 dB, Q is equal to 3, sorry, Q is equal to 4. If it is 3 surface, it will be 9 dB, Q is equal to 8. So, that way I can create. So, if I put a loudspeaker on the wall, surface wall, so directivity index is 2. If I put in a corner of junction of the 2 wall, directivity index is increased. So, that then direct power of the sound LP at the point R is nothing but a LW plus 10 log Q by 4 pi capital R square. R is the distance from the source. Okay. Now, what is reverberation sound? So, I said suppose this is the room and this is the source and this is the point I am calculating LP. So, this is the direct power plus reflected power, all reflected power will be there. So, what is the reverberant power or reflected power? So, it is LR is nothing but a LW plus 10 log 4 by A. A is the absorptivity in 7, 4 by A, 10 log 4 by A. Okay. Now, what is the total power at this point? LP plus LR. So, LP plus LR I can say it is nothing but a LW plus 10 log Q by 4 pi R square plus 4 by A. So, direct power, so this is LW will be remain same, LW is the LW. So, direct power is reduced by LW this and this will be added up. So, LW plus this one, okay, Q by 4 pi R square plus 4 by A. Now, if I say the condition is that, let us I define that find out the distance from the source or find out the distance from the source where the direct power which is Q by 4 pi R direct power and the reverberant power is equal. So, when it will be equal? When Q by 4 pi R square will be equal to 4 by A. So, a distance R is should be a critical distance where the direct sound power and reverberant sound power is equal. Let us the critical distance is DC, then Q by 4 pi DC square is equal to 4 by A, or I can say DC square DC is equal to root over of QA by 16 pi, 4 into 4 16 pi. So, it is root over of 16 pi. So, if I know the directivity factors and 7, I can find out the critical distance. I can find out the critical distance. Okay. Now, there is an interesting point in reverberation time. If you see, reverberation sound pressure level is LW plus 10 log A by 4 by A. If I increase A, the reverberation sound will be, this factor will be decreased. 10 log A, if A is large, then it will be minus. So, it will decrease. So, this can be used to noise reduction, change A from 47 to 107, what is the change in reverberation sound. What is the meaning of this is practical example is that suppose I want to install a machine in a room, okay, and machine created a noise. If I want to reduce the noise in that room, the machine which is created by the machine, so direct sound is there, the reverberation sound I can reduce. If I change A, then the reverberation sound field will be in. So, if the machine is installed in a reverberation field and if I change the A, then the noise created by the machine will be reduced in this particular point, because the reverberation power level will be decreased. Only the direct sound will be there. Direct sound is, so this can be used as a noise reduction. Okay. I have given one problem on that one, you can see that. So, now a critical distance. Then why the critical distance is important? I calculate the critical distance, I know, but why the critical distance is important? Why is critical distance important is the speech intelligibility. Suppose I design a lecture theatre, then I require a speech should be intelligible to every seat. I will define that speech intelligibility. For a distance from the source much greater than the critical distance, speech become increasingly more difficult to understand, because most of the sound energy come from reflection. So, I say once I go beyond the critical distance, what I said, the critical distance is a distance where the direct sound and reverberation sound is equal. Now, if I go that way, direct sound is less, reverberation sound is increases. So, now if I go such a point where the direct sound is become less and less and only the reverberation sound is there. So, percentage measure of Alcon, I will come on that, loss understanding of consonant. So, then the understanding of the speech is reduced, or intelligibility of the speech is reduced. A room with a reverberation time exceeding 1.6 second, there will be no listeners beyond 3.1 dc. After 3.1 time dc, there will be no listeners. He cannot receive the direct sound, only reverberation sound, and he is facing the problem of speech intelligibility. But if I put the loudspeaker on that area, then again it will be increases. So, when I design an auditorium, suppose I put only 2 loudspeaker in that stage and I know the directivity of that source and total power of the source, then I can calculate that directivity factor. Let the 2 loudspeaker only installed in the front wall of the stage, then I can easily calculate what should be the critical distance. Once I know the critical distance, 3.1 time the critical distance, after that nobody should be there. That means, I require a sound enforcement before 3.1 time critical distance. So, my next loudspeaker must be installed at 3.1 time of that critical distance within that time. So, I know where is my speaker's placement should be. I should not place a loudspeaker in the front wall, then within 1 meter another loudspeaker, within 1 meter another loudspeaker, which does not require wastage of acoustics power. So, I can put optimal distance loudspeaker, I can use that using the critical distance. Then critical distance is important for microphone placement also. Where I should place the microphone? It is general rule, a microphone should be no more than 0.3 dc for a omnidirectional mic and 0.5 dC for a directional mic. If I want to catch, then it should not be 0.3 dC for a omnidirectional and 0.5 dC for a directional mic. The loudspeaker and microphone should be at least as far as DC. To get a good audio systems in an auditorium, if I know that the critical distance of that auditorium, then the distance between the loudspeaker and microphone should be at least 1 dC. Okay. So, dC is important, that is why we have calculated the critical distance. Then effect of critical distance, it determines the maximum acoustic separation, it determines the ratio of direct to lower sound. So, this is very general statement, but critical distance is very important for placing the microphone when I put loudspeaker, and also the distance between the microphone and loudspeaker is very important. So, at least for when I design an auditorium, I should know what is the critical distance for that auditorium, depending on the, if I only place the speaker in the, let us place the speaker on the first in the front wall, then calculate the critical distance. Then once you know the critical distance, then you know the reinforcement required for that auditorium. Okay. So, let us stop here. Okay. Thank you.